Good morning, everyone. I'm Pubali does Sarkar, and I'm excited to welcome you to today's presentation. The focus is on computer science and engineering. Today, we'll be exploring some key concepts and ideas in this fascinating field. So, stay with me as we go through the main points and insights I've prepared. I hope you find this session engaging and informative. Let's get started. Let's dive into the concept of a stack. A stack is a fundamental data structure that follows a simple but powerful principle called last in, first out, or LIFO. This means that the most recently added item is the one that gets removed first, much like a stack of plates. Understanding how a stack operates is crucial. You push items onto the top of the stack and pop items off from the top as well. This simple operation makes stacks incredibly useful in various computing tasks, especially in managing function calls and undo mechanisms. Now, when it comes to implementing stacks, there are mainly two common approaches. One is using an array, which provides a straightforward way to store elements sequentially. The other is using a linked list, which offers dynamic sizing and flexibility, especially when the size of the stack isn't known in advance. It's also important to recognize the many applications of stacks. They're used in parsing expressions, backtracking algorithms, and even in managing undo features in software. Throughout this presentation, we'll see how these core principles and implementations come together to solve real-world problems efficiently. Let's talk about the basic idea behind a stack. A stack is an abstract data type, or ADT, which means it's a way of organizing data that defines certain operations and behaviors, but not how it's implemented. It's actually used in most programming languages, making it very fundamental. Now, the name stack comes from how it behaves in the real world. Imagine a deck of cards or a pile of plates. You can only add or remove items from the top. This is exactly how a stack operates. The last item added is the first one to be removed, which is a concept called last in, first out, or LIFO. This simple analogy helps us understand the core behavior of a stack and why it's so useful in various computational scenarios. Throughout this presentation, we'll see how this concept underpins many algorithms and data management techniques in programming. Let's take a closer look at how stacks can be represented in different ways. They can be implemented using arrays, which are simple and efficient for many applications. Another option is structures, which allow us to package data more flexibly. Pointers are also commonly used, especially when working with linked lists, which can make the stack more dynamic. Speaking of which, stacks can be either fixed in size or dynamic. A fixed-size stack has a set limit on how many elements it can hold, which is straightforward but less flexible. On the other hand, a dynamic stack can grow or shrink as needed, making it more versatile, especially in situations where the number of elements isn't known in advance. Connecting this to our overall theme, understanding these implementation methods helps us choose the best approach depending on the specific needs of our applications. Let's take a closer look at the core operations of a stack. First up is push. This operation adds an element to the top of the stack, kind of like placing a new book on the top of a pile. Next, create. This is how we initialize a new stack, setting up the structure to start adding and removing items. Then, we have pop, which removes the most recently added element. That's our last in, first out principle in action. It's also important to consider the state of the stack with isFull and isEmpty. isFull helps us determine if the stack has reached its maximum capacity, so we know when we can't add any more items. Similarly, isEmpty checks if the stack is empty, meaning there are no elements to remove. All these operations are fundamental because they demonstrate how stacks manage data efficiently, especially in scenarios like function calls or undo features in software. Understanding these key points helps us grasp how stacks function as a vital data structure in programming. So let's talk about the stack data structure, which operates on a last-in first-out, or LIFO, principle. This means that the most recently added element is the first one to be removed. Now, to work with stacks, we have several key functions. First, there's the push function, which allows us to insert an element into the stack. Think of it as placing a new book on top of a stack of books. Then, we have the pop function, which removes and returns the top element, like taking the top book off the pile. To start with a fresh stack, we use the create function, which initializes a new stack for us. It's important to check whether the stack is empty before performing certain operations, and for that, we have the isEmpty function. It simply tells us if there are no elements in the stack. Conversely, the isFull function helps us determine if the stack has reached its capacity, so we don't try to add more items than it can handle. Remember, for this implementation, we're assuming the stack contains integer elements. These functions form the core operations that enable us to efficiently manage data in a stack, which is fundamental in many algorithms and applications we'll explore later in the presentation. Today, we're going to look at how stacks can be implemented using arrays. A stack, as you know, is a data structure that follows the last in, first out principle. When we use an array to implement a stack, we essentially use the array's indices to keep track of the top element. The key idea is to maintain a variable, often called top, that indicates the position of the last inserted element. For example, when we push an element, we add it to the position pointed to by top, then increment top. And when we pop an element, we remove the element at the top one position, then decrement top. This way, the array acts like a stack, with the top variable managing the current position of the last inserted item. One important thing to remember is that with arrays, the size is fixed unless we implement dynamic resizing. So if the array becomes full, we need to resize it to accommodate more elements, which is a common extension. Using arrays for stacks is straightforward and efficient, especially when the maximum size is known in advance. It also allows for quick access to elements and easy implementation of stack operations. Overall, this approach ties into our broader discussion on data structures by illustrating how arrays can serve as building blocks for more complex structures like stacks. Now let's talk about pushing using a stack. When we say push, we're referring to the operation of adding an element to the top of the stack. Think of it like stacking plates. Every time you add a new plate, you place it on top of the previous ones. This is a fundamental operation in stack management because it maintains the last in, first out, or LIFO principle. The most recent item you added is always at the top, ready to be accessed or removed next. This concept is crucial across many applications, from undo functions in software to managing function calls in programming. So, pushing is essentially about placing new data onto the stack in a way that preserves the order and accessibility needed for efficient processing. All right, let's talk about the concept of pop using a stack. When we say pop, we're referring to removing the most recently added item from the stack. Think of it like a stack of plates. When you take one off, you remove the top plate. This is a fundamental operation in stack data structures. The key idea here is that stacks operate on a last-in, first-out basis, or LIFO. So whenever you perform a pop, you're always taking out the last element that was added. Understanding this operation is crucial because it underpins many algorithms and helps us manage data efficiently. Whether you're undoing an action in an application or managing function calls in programming, the pop operation is essential. Remember, the pop is always paired with push, which adds new items to the top of the stack. Together, these operations give us a simple yet powerful way to handle data in a structured manner. Today, I want to talk about stacking using a linked list. When we think about stacks, we usually imagine a collection of elements following the last in, first out principle. Now, instead of using arrays, we can implement a stack efficiently with a linked list. This approach gives us some advantages, like dynamic size, since linked lists can grow and shrink as needed without predefined limits. The core idea is to treat the head of the linked list as the top of the stack. So, pushing an element onto the stack involves creating a new node and making it point to the current head, then updating the head to this new node. Conversely, popping an element means removing the current head and updating the head to the next node in line. This method highlights how linked lists can be very flexible for implementing data structures like stacks, especially when we want efficient, constant-time push and pop operations. It connects to the overall theme of data structures by showing how different structures can be adapted to serve specific purposes efficiently. Now, let's talk about the push operation, specifically when we use a linked list. When we push an element onto a stack implemented with a linked list, we're essentially adding a new node at the beginning of the list. This means the new element becomes the new head of the list. This operation is quite efficient because it doesn't require traversing the entire list. It's a constant time operation, O1. The key point here is that the linked list structure makes the push process straightforward and fast, especially compared to array-based implementations. This aligns perfectly with the overall theme of our presentation, which emphasizes the flexibility and efficiency of linked lists for stack operations. So, in summary, pushing using a linked list involves creating a new node and updating the head pointer, making it a quick and effective method. Now, let's take a closer look at the pop operation, specifically when we use a linked list. When we perform a pop, we're essentially removing the top element from our stack. In a linked list implementation, this involves updating the head pointer to point to the next node. The key here is that we don't need to shift elements like in an array. Instead, we just adjust our links. This makes pop operations very efficient, especially for large data sets. Remember, the most important concept here is that by using a linked list, popping becomes a matter of reassigning pointers, which is a constant time operation. This ties into our overall theme of efficient data management, showing how linked lists can optimize stack operations by reducing the time complexity. In the array implementation, we start by declaring an array of a fixed size, which essentially sets the maximum size that our stack can grow to. This is an important point because it limits how many elements we can store, but it also makes access to elements very fast. We also keep a variable that always points to the top of the stack. Think of this as an index that contains the position of the most recently added element. By maintaining this index, we know exactly where the top element is at any given time, which makes push and pop operations efficient. Now, switching gears to the linked list implementation, instead of a fixed-size array, we maintain the stack as a linked list. Here, a pointer variable called top points to the start of the list. This means the first node in the linked list is always considered the top of the stack. This approach offers more flexibility because the size of the stack can grow dynamically as we add more elements, without worrying about a predefined limit. The key idea across both implementations is that the top element's position is always easily accessible, whether through an index in an array or a pointer in a linked list. This is what makes stack operations so efficient and straightforward. Now let's look at the declaration section. First, we define a constant maxsize and set it to 100, which will be the maximum size of our array-based stack. Then, we have the structure definition for a stack using an array. Inside the struct, there's an integer arraysint with size maxsize and an integer top to keep track of the current top position in the stack. We also create a type alias called stack for this structure for easier reference. Moving on, we see an alternative way to implement a stack using a linked list. Here, the structure includes an integer value and a pointer to the next node, which is also of type struct LIFO. This approach allows for dynamic memory allocation, meaning the stack can grow or shrink as needed, unlike the fixed size in the array implementation. We then create a type alias for this linked list node called stack as well, which might seem a bit confusing, but is common in C programming for simplicity. Lastly, we declare a pointer to a stack called top, which will serve as the top of our linked list stack. Overall, this slide highlights two fundamental ways to implement stacks, using arrays and linked lists, each with its advantages depending on the specific needs of the application. Understanding these foundations helps us choose the right data structure for efficient data management in our programs. All right, let's talk about stack creation now. When we create a stack, there are two common approaches. The first one involves initializing a stack using a pointer to a stack structure. In this case, we set the top of the stack to -1, which indicates that the stack is empty. Remember, the top points to the last element pushed in, so starting at -1 means nothing has been added yet. The second approach uses a double pointer, or a pointer to a pointer. Here, we set the pointer itself to null, which also signifies an empty stack. This method is often useful when we're working with dynamic memory allocation, especially in functions that need to modify the actual pointer passed in. Now, connecting this to our overall theme, whether you're working with arrays or linked lists, the core idea of creating a stack revolves around initializing the structure to an empty state. For arrays, it's about setting an index, like -1, while for linked lists, it's about setting the head pointer to null. Both methods ensure that your stack starts off correctly, ready for subsequent push or pop operations. Let's talk about pushing an element into a stack. In the array implementation, we check if the top has reached the maximum size -1, which indicates the stack is full. If it is full, we print a message saying, "Stack overflow," and exit the program. Otherwise, we increment the top index and assign the new element to that position in the array. Now, switching to the linked list implementation, the push function takes a pointer to the top pointer and the new element. We dynamically allocate memory for a new node. If the memory allocation fails, we print "stack is full" and exit. If successful, we assign the element value to the new node. Then, we link the new node to the current top by setting its next pointer to the current top. Finally, we update the top pointer to point to this new node. This approach allows us to push elements onto the stack dynamically without worrying about size limits, unlike the array implementation. Both methods effectively add elements to the stack, but they differ in how they handle memory and capacity constraints. Now let's look at how we pop an element from a stack. In the array implementation, the pop function checks if the stack is empty by seeing if the top index is. If it is, we display a message indicating a stack underflow and exit the program. Otherwise, we return the element at the current top position and then decrement the top index. This way, we're effectively removing the element from the stack. Switching over to the linked list approach, the process is a bit different. Here, we pass a pointer to the top pointer. First, we check if the top is null, which means the stack is empty. If so, we print a message and exit. If not, we store the value of the top node, then update the top pointer to point to the next node, and free the memory of the old top node. Finally, we return the stored value. The key takeaway is that both methods manage the pop operation by removing the most recently added element, but the implementation details differ based on whether we're using an array or a linked list. This illustrates how data structures can be adapted to different scenarios while maintaining their core behavior. Let's talk about how we check if a stack is empty. In the array implementation, we usually keep track of the top index. If top is -1, it means there are no elements in the stack, so it's empty. That's when we return 1, indicating true. Otherwise, if top is not -1, the stack has some elements and we return 0, meaning it's not empty. Now, for the linked list implementation, the idea is similar but uses a different approach. Here, we check if the top pointer is null. If it is, that means there are no nodes in the list, so the stack is empty. We return 1 in that case. If top isn't null, then the list has elements, and we return 0. The key takeaway here is that regardless of whether we're using an array or a linked list, the fundamental concept is to check whether the top indicator, be it an index or a pointer, is in its initial empty state. This check is crucial for controlling stack operations safely and correctly, tying back to our overall theme of understanding data structures and their management. Now let's talk about how we check if a stack is full or empty. On this slide, you'll see 2 different implementations for checking if a stack is empty, depending on the underlying data structure. First, for an array-based stack, we use the function isempty that takes a pointer to the stack. It checks if the top index is equal to -1, which indicates that the stack is empty. If it is, we return 1, meaning true for empty. Otherwise, we return 0. Next, for a linked list-based stack, the approach is slightly different. Here, the isempty function takes a pointer to the top node. If this pointer is null, it means there are no elements in the stack, so we return 1. If it's not null, then the stack contains items, and we return 0. The key takeaway is that, regardless of the data structure, whether array or linked list, the core idea is to check a specific condition that tells us whether the stack is empty. This is crucial because it prevents errors like trying to pop from an empty stack, which can cause bugs or crashes. So, understanding these checks is fundamental to managing stacks safely and efficiently, especially as part of larger algorithms or systems we build. It ties into the overall theme of ensuring robust data structure operations. Let's look at this example of a stack implemented using an array. Here, we start by including the standard input-output library and defining a maximum size for our stack with maxsize set to 100. We then define a structure called LIFO, which contains an array sent to hold the stack elements and an integer top to keep track of the current position in the stack. We also create a type alias stack for easier reference to this structure. In the main function, we declare two stacks. A and B, we initialize both stacks with a create function, which sets them up to be empty. Then we push a few elements onto each stack, 10, 20, and 30 onto stack A, and 105 onto stack B. Next, we demonstrate popping elements from both stacks and printing them. The first print outputs the top elements from each stack, which are 30 from A and 5 from B. Then, we push the element popped from B back onto A, showing how stacks can be manipulated dynamically. Finally, we check if stack B is empty using the isEmpty function. If it is, we print a message indicating that B is empty. This example highlights the core operations of a stack, push, pop, and checking if it's empty, implemented with arrays. It's a practical way to understand how stacks work under the hood, especially in terms of managing data with a last-in, first-out approach. This connects to our overall theme of understanding data structures and their applications in programming. Let's take a look at this example of a stack implemented using a linked list. We start by defining a structure called LIFO, which has an integer value and a pointer to the next node. Next, this structure allows us to create a linked list where each node holds a value and points to the next node in the stack. We then create a new type called stack as an alias for struct LIFO for convenience. In the main function, we declare two stack pointers, A and B, which will serve as our two separate stacks. Using the create function, we initialize both stacks to be empty. Next, we push three values onto stack A, 10, 20, and 30 in that order. Similarly, we push two values onto stack B, 105. When we print the result of pop and A and pop and B, it shows us the last element added to each stack, so 30 from A and 5 from B. Then we push onto the value we just popped from B, which is 5, so now A's top is 5. Finally, we check if B is empty using isEmpty B. If B has no elements, we print that B is empty. This example demonstrates the core operations of a stack, push, pop, and checking if the stack is empty, implemented through linked lists, which makes the stack dynamic in size. It's a great way to understand how linked data structures can efficiently manage stack behavior without predefined size limitations. Now, let's explore some of the practical applications of stacks. First, on the direct side, stacks are used to keep track of the page visited history in a web browser. Every time you visit a new page, it gets pushed onto the stack, and when you hit the back button, the browser pops the previous page off the stack to display it. This makes navigation intuitive and efficient. Another common use is the undo feature in text editors. Each change you make is pushed onto a stack, so when you undo, the most recent change gets popped off, restoring the previous state. This LIFO behavior is perfect for undo operations. Stacks also play a role in the Java virtual machine, especially in managing the chain of method calls. When a method is invoked, its context is pushed onto the call stack, and once it completes, it's popped off, ensuring smooth execution flow. Additionally, stacks help in validating XML files. They assist in checking whether tags are properly opened and closed, maintaining the correct nesting structure. Now, on the indirect side, stacks serve as auxiliary data structures to support various algorithms. For example, they help in parsing expressions or backtracking algorithms. They are also fundamental components of other data structures, such as implementing queues or graphs, or even in more complex structures like trees and heaps. Overall, stacks are incredibly versatile. They're not just a standalone concept, but a building block for many computational processes we rely on daily. Let's take a look at infix and postfix notations. In infix notation, which is what we're most familiar with, operators are placed between operands. So, for example, we write a plus b times c as a plus b times c. This is the natural way we usually write expressions. On the other hand, in postfix notation, also known as reverse Polish notation, the operands come first, followed by their operator. So the same expression would be written as ABC times plus. Notice how the order changes, but the meaning stays the same. One of the key advantages of postfix notation is that there are no precedence rules to memorize. You don't need to worry about parentheses for order of operations because postfix inherently specifies the order. This simplifies the process of evaluating expressions, especially in computer algorithms. Overall, understanding both notations helps us appreciate different ways to represent and evaluate expressions efficiently. Postfix notation, in particular, makes parsing and computation more straightforward without the need for parentheses or precedence rules. Now, let's take a closer look at how infix expressions are converted into postfix notation. As you can see in the table, the infix expression a plus b becomes a b plus in postfix. This straightforward conversion is key because postfix notation removes the need for parentheses, making evaluation simpler for computers. When dealing with more complex expressions, like a plus b times c, we see it transformed into a bc times plus. Notice how the multiplication has higher precedence, so b and c are grouped together first, then added to a. For expressions with parentheses, such as a plus b times c, the parentheses indicate that a plus b should be evaluated before multiplying by c in postfix. This becomes a b plus c times. The parentheses are no longer needed because the order of operations is encoded in the postfix sequence. Let's look at a longer example. A plus b times c plus d in infix, parentheses clarify the order, but in postfix, it becomes a bc times plus d plus. Here, b times c is evaluated first, then added to a, and finally d is added. Similarly, for expressions like a plus b times c plus d, the postfix version is a b plus c d plus times. Each parenthesis's operation is captured by the sequence of operators following their operands. Now, consider the expression a times b plus c times d. Its postfix form is a b times c d times plus. Notice how the multiplications are evaluated first, then the addition. This illustrates how postfix notation preserves the operator precedence naturally. Finally, let's walk through a more detailed example. A plus b times c in infix, it's a plus b times c. When converting to postfix, it becomes a bc times plus. The parentheses are implicitly handled by the order of the operators. Similarly, a plus b times c plus d converts into a bc times plus d plus in postfix. This step-by-step transformation helps us see how the sequence of operators encodes the original expression structure, simplifying the evaluation process. Overall, understanding these conversions is crucial because they allow us to process and evaluate mathematical expressions efficiently, especially in computer algorithms. Now, let's take a closer look at how infix to postfix conversion works using a stack. The core idea is that we process operators and operands sequentially from left to right, just like reading an expression naturally. We use a stack specifically for handling operators, which allows us to manage precedence and associativity efficiently. As we scan through the expression, when we encounter an operand, we simply output it immediately. When we encounter an operator, we compare its precedence with the operator at the top of the stack. If the operator on the stack has higher or equal precedence, we pop it and output it, continuing this process until the top of the stack contains an operator of lower precedence. Then, we push the current operator onto the stack. This approach ensures that operators are arranged correctly in the postfix expression according to their precedence, which is crucial for accurate evaluation later on. Remember, the key points here are the use of a stack for managing operators and the step-by-step comparison to maintain the correct order. This method is fundamental to understanding how expressions are transformed from infix to postfix, connecting directly to our overall theme of expression evaluation and efficient computation. Let's walk through the key steps of the algorithm. First, we print operands as they arrive, so every number or variable gets output immediately. When it comes to operators, if the stack is empty or there's a left parenthesis on top, we push the incoming operator onto the stack. This helps us keep track of operators in the correct order. Similarly, if the incoming symbol is a left parenthesis, we push it onto the stack to mark a new subexpression. Now, if we see a right parenthesis, we pop operators from the stack and print them until we encounter a left parenthesis. We then discard that pair of parentheses, since they're just structural markers. When an incoming symbol has higher precedence than the top of the stack, we push it onto the stack to ensure higher priority operations are performed first. In cases where the incoming symbol has equal precedence, we need to consider associativity. If the association is left to right, we pop and print the operator on top of the stack before pushing the new operator. If the association is right to left, we simply push the new operator without popping. This maintains the correct order of operations. If the incoming symbol has lower precedence than the top of the stack, we pop and print the top operator, then compare again with the new top, repeating this process as necessary. Finally, at the end of the expression, we pop and print all remaining operators on the stack, ensuring no parentheses are left and the expression is fully converted. These steps together form a systematic way to process infix expressions into postfix notation accurately. Now, let's look at the key points involved in converting an infix expression to a postfix expression. First, we need to understand that operator precedence information is essential for this process. Without knowing which operators take priority, we can't correctly convert the expression. When we encounter operands, we simply add them to the postfix expression. They are straightforward and don't require any special handling. Next, let's consider what happens when we see a close parenthesis. This signals us to pop symbols from the stack until we find an open parenthesis. This ensures that the entire subexpression within the parentheses is correctly handled and added to the postfix expression. For operators, the rule is to pop all stack symbols until we find one of lower precedence. This step ensures that higher precedence operators are processed first, maintaining the correct order of operations. After clearing out higher or equal precedence operators, we then push the current operator onto the stack. Finally, when we reach the end of the input, we need to pop all remaining symbols from the stack and add them to the postfix expression. This guarantees that all operators are included and the conversion is complete. These steps form the core logic of the infix to postfix conversion process, and understanding them helps us accurately translate expressions in a way that computers can efficiently evaluate. Let's walk through this table step by step to understand how the expression is converted from infix to postfix notation. Starting with the initial symbol, which is 1, we see that the operator stack contains A, and the postfix string is just A. When we encounter 2, which is asterisk, we push it onto the stack, so now the stack has asterisk and A, and the postfix remains A. Next, when we see an opening parenthesis, we push it onto the stack as well, making the stack now asterisk and A. Moving on to B, which is a variable, it gets added to the postfix, so the postfix string becomes a B. When we encounter plus, since the top of the stack is, we push plus onto the stack, so now the stack is asterisk, plus an A. Then we see C, which is another variable, so we add C to the postfix, making it ABC. Next comes asterisk, which has a higher precedence than plus, so we push onto the stack. The stack now contains asterisk, plus, A, and B. Seeing D, we add it to the postfix, so the postfix string updates to a BCD. When we encounter a closing parenthesis, we pop from the stack until we reach the corresponding. This means we pop asterisk and plus, adding them to the postfix, resulting in A, B, C, D plus. Now the stack has asterisk left, which we remove, leaving us with. Next, we see plus, which has lower precedence than asterisk. So we pop asterisk from the stack and add it to the postfix, making it a B, C, D. We then push plus onto the stack. When we see E, we add it directly to the postfix, giving us a B, C, D, E. Finally, when we process the last operator, plus, we pop plus from the stack and add it to the postfix, resulting in the final postfix expression, a B, C, D, E plus. This process effectively rearranges the expression into reverse Polish notation, which is very useful for computers because it eliminates the need for parentheses and makes evaluation straightforward. Remember, the key rules are about operator precedence and parentheses, which guide how we push and pop operators on the stack. This conversion is fundamental in understanding how expression evaluation works behind the scenes in many programming languages and calculators.